Hello, my name is Taylor Ross. I'm an Aximmetry ambassador and the owner of Frustum Virtual in Los Angeles, California. In this tutorial, I'll be showing you how to use Aximmetry DE Composer for LED In-Camera VFX. So the first thing that we need to do is launch Aximmetry DE Composer. Once Aximmetry launches, you'll see the Aximmetry Composer startup configuration. This first page is our video outputs. You'll see our video output devices. I have 3 monitors connected directly to my graphics card via HDMI, 2 desktop monitors, and 1 TV. The TV will be acting as the LED volume for this tutorial. Below that, I have my Blackmagic Decklink 8K Pro. I know that my live camera feed will be coming in on Blackmagic Decklink 8K Pro 1, and that my final pixel output will be going out on Blackmagic Decklink 8K Pro 2. My final pixel output will be index 2, and my preview monitor will be index 1. My preview monitor is my secondary desktop monitor. I will set my TV or LED volume to index 3. Normally, you can send all the LED wall images merged into a large frame through a single HDMI or DP cable, and the LED wall processor will send everything to the right place. The LED wall processor will report the total size of the frame, as well as the expected frame rate for your PC. This will appear as a monitor of the right size both in Windows and in Aximmetry. For this tutorial, I have a TV that will be acting as the LED volume. I've set the index of this monitor to index 3. I will also need to set sync for this output. Now if I quickly open my display settings in Windows, as I mentioned before, all of our LED wall images will be merged into one large frame through a single HDMI or DP cable. This will appear as a monitor of the right size both in Windows and in Aximmetry. So in Windows, you can see that my output is 3840 by 2160. I will now close my display settings and go back to Aximmetry. Here in Aximmetry, you can see that same monitor, 3840 by 2160 at 24 frames per second. So I've set that to index 3. If you are sending multiple video signals through HDMI or DisplayPort cables, you can index these outputs to 3, 4, 5, and above. Just make sure that you're setting sync on the first HDMI or DisplayPort output. For this tutorial, I'll only be using a single machine configuration. There will be a link in the description that will take you to the documentation to show you how to set up a multi-machine configuration. The setup of a multi-machine configuration is almost identical to a single machine configuration. The main difference is that there will be a central machine setup and then remote engine setups. In future tutorials, I will cover the setup of the multi-machine configuration. If you are setting up a multi-machine configuration, you can still watch this tutorial because the setup will be almost identical to this setup. Now that we have the TV that will be acting as our LED volume mapped to index 3, we can navigate to the device mapper on the left-hand side. The device mapper page is where you can set up presets for all of these different categories. With the video category selected, I can use this dropdown to create a preset that will launch every time that we open Aximmetry. We can set any of our Blackmagic inputs to be presets when we launch Aximmetry DE Composer. I'm not going to set any presets in this tutorial because I want to be able to show you how to set these settings once Aximmetry DE is already open. If you would like to create a preset, this is how you do it. Now on the left-hand side in our categories, we'll select camera tracking. With camera tracking selected, we can select manage devices at the bottom. We can now scroll down in these settings, find game. Under game, we have OpenVR, which is the HTC Vive, and then we have anti-latency, which is the anti-latency system. Below that, we have camera tracking, which is all of the camera tracking solutions that are available with Aximmetry DE. I will be using the anti-latency system for my camera tracking solution. In the anti-latency section, you can see this use device is already populated with camera 0. This is the device that's already connected to my computer. Once you select your device, you can just select apply and then OK. The last category that I will talk about in the device mapper is the zoom encoder. The zoom encoder will also be used for focus encoding. So with the zoom encoder category selected, I will then select manage devices. Now we can scroll down on the left-hand side to the zoom encoder section. These are all the different zoom encoder solutions that are available with Aximmetry DE Composer. For my zoom encoder, I will be using the Glassmark lens encoder. This lens encoder is run by the LowNet 2 server, so I will select that. If this is your first time setting it up, you can select Add in the upper right-hand corner. You will then need to input the UDP port and join multicast group. I will quickly open my LowNet 2 server just to show you that the UDP port and multicast group match. Now I will minimize the LowNet 2 server and keep it running in the background. Since this is already set up, I'll hit cancel and then I'll hit OK. In the upper left-hand corner, I'll navigate back to my video outputs page. All of my video output devices are mapped properly. Now I can select apply and start. Once Aximmetry loads, the first thing that you'll see is this blank sequence editor. The first thing that we need to do is add a new compound, so we'll come up here to New, Compound, or Control-N on the keyboard. Now on the left-hand side, under Projects, we'll find Common Studio, Camera, and then we're looking for LED Wall Cam. I'm going to add the LED wall 3cam 4 wall to this project. So I will just click and drag the LED wall 3cam 4 wall directly into the compound. Now we need to add the custom Unreal Engine project that we created in another tutorial. Navigate to the file browser. By default, this should be in Documents, Unreal Projects. The custom Unreal Engine project that I created is called Aximmetry LED-01 with the 5.3 at the end. We'll open this. Now we will just click and drag this Unreal project directly into the compound. Once this project loads, you'll see that there are pins on the left-hand side that match the pins of our LED wall 3cam 4 wall. We'll click and drag from outsize to outsize and from control data to control data. On the right-hand side of our custom Unreal Engine project, we have pins that match the pins on the left-hand side of our LED wall cam. We'll click and drag from out to rendered, F1 to F1, F2 to F2, F3 to F3, and F4 to F4. Finally, we need to connect our outputs. On the right-hand side of our LED wall cam, we're going to click and drag from preview to the output bar on the right, out to the output bar on the right, LED wall 1 to the output bar on the right, LED wall 2, LED wall 3, and LED wall 4. When we added the LED wall 3cam 4 wall to our compound, it added these tabs at the top. We have flow, cameras, inputs, and LED walls. I'm going to select this cameras tab at the top. You'll see this select camera square. We have cam 1, cam 2, and cam 3. These correspond to our inputs tab, input 1, input 2, and input 3. So in our cameras tab with camera 1 selected, we will be affecting inputs, input 1. All of the settings for input 1 will be located next to this input 1 square. When we select this input 1 square, all of the settings will populate on the right-hand side. The first setting in this list is camera device. If I drop this down and select my Blackmagic Decklink AK Pro 1, I know that this is my live camera feed. Now in preview 1 and 2, I will be able to see the live camera feed from my physical camera. Now back on the right-hand side, under camera mode, I will select these 3 dots. This is where I can change the resolution and frame rate of this camera feed. I know that my camera is sending a 1080 at 24 frames per second. You could also leave this on auto. Next, I will drop down this tracking device. I'm going to be using my game anti-latency camera 0, so I'll select that. Now for my calibration profile, I'm going to use these 3 dots to select the calibration profile that we created in another tutorial. This is the 18mm red helium 8K. If you need help setting up your calibration profile, we have another tutorial that covers this entire process. For the zoom device, I'll drop this down and select the LowNet 2 server. Now that we have our input 1 camera settings set up, there are a few more settings that we will change. The main settings that I want to talk about in this tutorial are the detect AR tracking delay and detect AR zoom delay. These are auto detect functions for our tracking and zoom delays. When I turn on this detect AR tracking delay, we will see a red square on our LED wall. We will use this square to detect the tracking delay of our camera tracking. There will be overlays on the screen to guide you through this process. Once Aximmetry recognizes this red square, it will ask us to rotate the camera left and right, panning. We will just pan our camera back and forth. Once it finds the delay, it will say delay found in set, minus 3.4 frames. Aximmetry will also auto-populate the AR tracking delay. You can see that it is now 3.4 frames. Below the detect delay settings, we have this tracking dejitter. This would be used to remove the jitter from your camera tracking. The anti-latency system is very stable, so I don't need to turn this on. If you notice a lot of jitter in your tracking data when your camera is still, you can turn this function on, and then you can adjust the dejitter position and dejitter rotation. For this tutorial, I'm just going to leave this off. You will need to experiment with these settings in your own project. If you're using a zoom lens, you can use the detect AR zoom delay. This is the same as the detect AR tracking delay, except you will zoom your camera in and out. Now that all of our input 1 settings are set up, I'm going to talk about the rest of the input 1 settings. Next to input 1, we have vignette 1, keyer 1, adjuster 1, and origin 1. Above these settings, we have a scene tab. Vignette 1 is used to detect the vignette of your lens. If I turn this on, I will need to capture a vignette. So I'll select this vignette square. In order to capture the vignette, we need to turn on this capture vignette setting. So with this on, Aximmetry will walk you through the process of capturing your vignette. For this tutorial, I won't go through the process of capturing a vignette. The process is pretty straightforward with the on-screen prompts from Aximmetry. Next to the vignette setting, we have keyer 1. If I turn this on, it will key out anything that's green in my frame. This is similar to what we talked about in the tracked camera and mixed camera compounds. With keyer 1 selected, I can change my monitor mode to input, and then I can select my background color using this green square. Select the green square, and then find the eyedropper in the lower left-hand corner. Click and drag this to the green color of my green screen. Change the monitor mode to matte, and then adjust my low cut and high cut values until the black is completely black and the white is completely white. Then I can change my monitor mode to final. In the tracked camera and mixed camera tutorials, I go over this in more depth, but here in preview 1 and 2, you can now see that the green screen is being live keyed. This is really powerful if you have a green screen around your LED volume. Once we get into the LED walls tab, you'll see that there is also a keyer in that section. I'll go over those settings once we're in the LED tab. I'll go ahead and turn off this keyer 1. Next to keyer 1, we have adjuster 1. This is a color correction for input 1. So if I change the brightness, you'll see that it's affecting the brightness of the entire input. Adjuster 1 will be our color correction for input 1. So adjuster 1 is the color correction for all of input 1. There's also an adjuster in the LED tabs. The adjuster in the LED wall tab is the color correction adjustment for just the LED wall. The final setting that I will talk about in input 1 is this origin 1. So if I select origin 1, this will allow us to set the origin of our scene. Just like in the tracked camera and mixed camera tutorials, setting the origin is the first step in our studio calibration. I can set the origin of our input 1 by placing an ArUco marker on the floor, tilting my camera down to the ArUco marker, and then selecting Detect Origin. There will be a link in the description to this ArUco marker if you need it. With the ArUco marker in the view of my camera, I can select Trigger next to this Detect Origin. This will set the origin for my tracking volume. The final settings that I will talk about in our Inputs tab is the Scene Settings. This is where we can adjust the position of our scene. So with this orange scene square selected, you will see the settings for the scene on the right-hand side. We can then click and drag the Basecam transform, position, and rotation in order to position ourselves in the scene. As I mentioned in the setup of the custom Unreal Engine scene, you will always start at the world 0 of your level. So in order to move in the scene, you need to use these scene settings. If you watch preview 1 and 2, when I click and drag the Basecam transform position, this is updating the position that we're in the Unreal scene. This custom Unreal scene was built from World 0, but if your custom Unreal Engine scene wasn't built from World 0, you'll need to adjust these scene settings. Now that I've covered all of the Input tab settings, we can navigate to the LED Wall tab at the top. In the LED Walls tab, you will see LED Wall 1. When we select this, this will open the settings for the LED Wall 1 on the right-hand side. The first thing we need to do is make sure that the LED wall is the proper size and that it's placed in the proper position. If the LED wall is not in front of our camera in the virtual scene, we can use this put in front trigger. We have put distance, auto place, transform, size, curve radius. Curve radius is used if you have a curved LED volume, resolution, shape, shape mask, Frustum, fill resolution multiplier, fill blur. A lot of these settings will only affect the LED wall itself. The first thing that we need to do is find the size of our LED volume. You will need to measure the length and height of your LED volume. This will be translated in meters. I can navigate to my LED wall 1 and select check. This will put this checkerboard pattern on the screen. Each one of these squares, 3 and a checkered square, is 1 meter. So the default size setting of 4 by 3 is 4 by 3 meters. This is much larger than the screen that I am using. In the LED wall tab, we have the Studio tab. If we turn on this light bulb, it will give us a virtual overlay of the size of the screen that's currently in the scene. Next to this light bulb, we have a mouse. If we turn this on, it will give us a 3D view of our scene. We can now see the size and location of the screen that's placed in our virtual world. The default 4 by 3 meter square that's added in the virtual world is way too large compared to the screen that I'm actually using. So on the right-hand side of our LED Wall 1 settings, I need to input the proper LED wall size. I will navigate to the size setting on the right-hand side. I've already taken these measurements and the true size of my screen is 1.2192 by 0.6858. I will just input these values in the size setting. Remember that this is in meters. Now in my preview 1, you will see that the size of the screen is a much more accurate representation of the size of my screen in the physical space. You can also see in preview 2 that the aspect ratio of this screen is incorrect. We will need to update the resolution to the proper resolution. So the resolution of this screen is 3840 by 2160. I will navigate to the resolution setting and input 3840 by 2160. Now in preview 2, you will see that the screen has a perfect overlay of this checkerboard pattern. By default, the screen is already placed on the floor. We will need to place the screen in the same position that it's in the physical world. To see this a little bit better, I will turn off the mouse in Studio. You can now see the placement of the virtual screen compared to the physical screen. The goal here is to get the virtual screen to overlay perfectly on the physical screen. If your screen is not visible in this view, you can start by using this put in front trigger. This will put the screen in front of the view of your camera. Next, we will use this auto place trigger. This will display an ArUco marker on our screen, and then it will place the virtual screen over our physical screen. So I will just select this auto place trigger. We'll see the ArUco marker, and then we will see that the overlay matches both on our physical volume and in our virtual world. This placement should be very specific for your volume. So if your resolution and size are correct, you shouldn't see any ghosting. I can now make some slight adjustments to my transformation. I just want this overlay to be perfect so that the one and these checkerboard patterns line up perfectly with no ghosting between the two images. As I continue to adjust these transformation settings, you will see the ghosting that I am talking about. So you just want to get this virtual overlay to match your physical screen's overlay perfectly. Again, with this auto place function, this shouldn't be an issue for most volumes, so you may not need to make any further adjustment, but if you notice any ghosting, you can slightly adjust the transformation to get it perfect. So now if I navigate back to the Studio tab and turn on the mouse, I can see that this is a much more accurate representation of the placement of my screen in my physical space. Once you're happy with the placement of your virtual screen in the virtual world, it should match the physical world. We can now navigate back to the Studio Square and turn off this mouse. We can also turn off this light bulb. Now in our LED Wall 1, we can switch from check to final. Now our studio should be calibrated between the virtual and physical worlds, so the view from the camera will be much more specific. If you have multiple LED screens in your volume, you will be able to do this for every single LED wall. You can just turn on the LED walls that you will be using, LED Wall 2, LED Wall 3, and LED Wall 4. You will then need to set the size and resolution for each of these screens, as well as the placement. Since I only have one LED wall, I'm going to turn off all of these LED walls. I will turn off the mouse and the light bulb in my Studio Square. Next to LED Wall 1, we have an adjuster. This adjuster will be the color correction for the LED wall only. With adjuster 1 selected, I will be affecting the color of LED Wall 1. I will adjust the brightness here so that you can see the effect. For this tutorial, I'm not going to do any crazy color correction. I will just set my brightness to something like 1.2 so that we can see the LED screen a little bit better. Next to adjuster 1, we have fill adjust 1. This will be the color correction settings for the fill. The fill is the area outside of the frustum or the view of the camera. The fill adjustment will only affect the fill outside of the frustum. So if we select this and change the brightness, you won't be able to see this in this tutorial, but just mess with this setting in your own project. My preview 1 and 2 are only showing you the frustum view. So this is the view of the camera. Everything outside of this view is called the fill. Next to our fill adjustment 1, you will see green. If I turn this on, it will turn the frustum view green. We can then turn on the previs keyer. This will remove anything that's green in our camera's view. Remember that this is different than the input 1 keyer. I'll go ahead and turn off previs keyer and green. Above this setting, we have digital extension and digital extension adjustment. I will turn on the digital extension. This will extend the virtual world around our LED volume. This is an extremely powerful function that is not available using in-display. We're able to do digital set extension and Aximmetry because of how calibrated our studio is to our LED volume. Because Aximmetry is so specific in placing our screen in our virtual space, we are able to do digital set extension. The digital extension adjustment is a color correction tool for adjusting everything outside of our LED wall. You can see that the color of my LED screen doesn't really match the digital set extension. We have 3 different adjusters that we can use, 2 in the LED wall and 1 in our inputs tab. The adjuster in our inputs tab is affecting the entire image. The adjuster next to LED wall 1 is adjusting the LED color. And then our digital set extension is being adjusted by digital extension adjustment. So using these 3 adjusters, we should be able to match the color between our LED wall and our digital set extension. I'm not going to go crazy with the color correction for this tutorial, but feel free to experiment with all of these settings in your own project. Another color correction tool that we have is this LUT measure. You can use the LUT measure setting to create a LUT for your LED wall. You just simply turn this setting on, and then there will be on-screen prompts that will guide you through the entire process of creating a LUT for your LED wall. I'm not going to go through the LUT measure calibration in this tutorial, but feel free to experiment with this in your own project. Just remember that when using digital set extension, you're going to want to calibrate the color between your LED volume and your digital set extension as closely as possible. I will quickly select this digital extension adjustment and make some adjustments to the color to show you what it does. As I mentioned before, I'm not going to go crazy with color correction in this tutorial. This is just something that you'll have to experiment with in your own project. Just remember that adjuster 1 is only adjusting the LED wall, and digital extension adjustment is only the digital extension. To the right of our digital extension adjustment, we have an AR overlay. If you've set up any elements in your Unreal scene to be AR elements, you can turn this on. and it will overlay the AR elements over your LED volume. The last two things that I'm going to talk about in this tutorial are Frustum. Frustum is the view of the camera. We have a vertical resolution, which is the resolution of the Frustum. If you need the resolution of the Frustum to be higher, you can set this vertical resolution to something like 2160. You will notice that the processor load is being impacted by this resolution. Depending on the scene that you're running, you may be able to run this at 3840 by 2160. For this tutorial, I'm going to set my vertical resolution to 1920 by 1080, but remember that the vertical resolution is the resolution of the Frustum. I'll just go ahead and set my vertical resolution back to 1080 to save on the processor load. That will just make sure that I'm getting the frames per second that I need for this tutorial. We're back to 24 frames, and my GPU isn't getting capped out. Most of the time when you're shooting on an LED volume, the LED screen itself won't be in focus, so you don't need to set this resolution extremely high. A lot of this will depend on the scene itself, so this is just another setting that you'll have to experiment with for your scene. Below the vertical resolution setting, we have an edge expand setting. This will expand the edges of your Frustum. If you are panning or moving your camera really quickly in your scene, and you notice that you're seeing the edge of your Frustum, you can use this edge expand setting. Try not to go too crazy with the edge expand setting because it will also impact the processor load. You will just want to increase this in 0.1 increments, and then you can quickly pan your camera back and forth to see if you're still catching any of the edges of your Frustum. Also keep in mind that the vertical resolution will be multiplied by this number, so depending on how high you set this edge expand setting, you will see that it is impacting your processor load. Next to the Frustum square, we have the fill square. This is where you can adjust your fill settings. You have used fixed position. You can also capture the fixed position, and then there's a freeze option. All of these settings will help you offset the processor load. You can experiment with these settings depending on what your Frustum settings are. The final settings that I will talk about are back in our LED Wall 1 panel. On the right-hand side, we have Fill Resolution Multiplier and Fill Blur. The Fill Resolution Multiplier will allow us to multiply the resolution of the fill. In most cases, I will leave this at the default 0.5. This is another setting that you can experiment with if your processor load is too high. We can also blur the fill with this Fill Blur setting. It will be hard to showcase this in this tutorial because you're only seeing the Frustum view. Just know that this Fill Blur setting will blur the fill for you. This is another setting that can help you offset the processor load to give you more frames per second and more room on your GPU. Again, this is another setting that you'll have to experiment with in your own project. Lastly, we have Fill Freeze. This will freeze the position of your fill. Again, go ahead and experiment with these in your own project and see what fits your project best. With everything that we've covered in this tutorial, you should have a pretty good understanding of how to use Aximmetry DE for LED Wall In-Camera VFX. The last thing that I will do before closing Aximmetry DE Composer is come up here to File, Save As. I can then save this project in Studio Calibration. With this project saved, I can now swap out Unreal Engine projects, and I won't have to go through this calibration process again. Once the project is saved, I can just close Aximmetry DE Composer. Hopefully this video was helpful in getting you started with Aximmetry DE Composer for LED In-Camera VFX. Be sure to like and subscribe for more videos, and thanks for watching.